I think.
Yeah, it makes sense.
But now we need to turn it off.
Turn the volume off on, right?
Yeah. You can watch that as well. Hello? Yes. Why is this still? I think that should work now. Hello? Oh, you're on the call? Okay, that's fine. I thought it was a microphone speaker at the back of the room. Okay, that's fine.
So it's all just through the iPad now then?
But the presentation.
Coolio. Okay. Hey, if it works, it works.
Sorry about that.
You get your money back from Zoom.
Yeah. Where's the union money now? Yeah, £12 a month.
God, you may want to move these.
I used to burn a credit card for it, so it can never charge me that.
We can do it. Put it off. I have no idea. Good. It's sort of obstructing the camera view.
It's like you have a subscription because and I'm like, yeah.
Nice, but we don't talk about the narrow point.
They have it in physics. I think there's the 2 departments left with like old-fashioned blackboards.
Oh, the blackboards were amazing. They were like
Huge and it's
yeah, like sliding. Yeah.
I might change my name on there. Temporarily possible name. Just so it's less confusing.
Yeah. Or just group present or something.
Yeah.
I took the lift and then the stairs and then got lost.
How do I do this? Spell your name.
Does it not?
Presenter 1.
Okay.
It wanted a second name. I could have the presenter.
It hasn't updated, but
Oh dear. What if I leave and join?
people are trying to join the room as well.
Work out how to just disable the wait.
Okay. Never leave this.
Be about 40 odd minutes and then have some questions.
I think our hard cut was 2:15.
Okay.
That's no record. So 3:30.
Yeah. I think I have a meeting at 3, which I'll take from a cafe or something.
It's really complicated.
Yeah. That was kind of cool.
Christoph, I'm gonna make you the host, which means can you like let people into the room?
Oh, yes.
That's the easy section.
Shouldn't have done
And
that.
I'll help you with
Because I can't.
okay, just come on. Where's this beautiful mash interfaces again? Yeah,
I clicked the wrong person. So how do I reclaim her?
Can you?
There we go. Okay.
I can just
Yeah.
let people in if I see them.
Let's get started. Yeah.
Did you make me host?
No, I didn't. It's fine. This should work. Okay.
Okay. Shall we get started? So those on, hopefully you can hear me. We have an interesting IT setup. And hello to everyone in the room. So my name is Dr. Thomas Clayson. I'm the founder and CTO of Magdrive. Go give a quick introduction to myself and then talk about my presentation about the future of where space is going and how you can pursue jobs in the space industry if you're interested. So I did my PhD and my master's here at Imperial. I was in the Blackett lab across the way, I guess. I graduated from my master's in 2014 and then did my PhD in the Magpie pulse power generator underground, which was great fun, in the wonderfully titled field of plasma laboratory astrophysics, which basically means we were blowing things up with large amounts of electrical power to, we claimed, simulate astrophysical events on like a much smaller scale, and then scale up several orders of magnitude. It was great fun though. Then went to go work at First Light Fusion, which is a VC-backed fusion company trying to commercialize fusion as a power source to power all of our electronics and so forth. Helped design and build the M3 pulse power machine, which is the largest operational pulse power machine in Europe. And then 2020 came along, there was a pandemic, and I said to my wife, you know what? I'm going to leave my job and start my own company. And she wasn't happy with that, but it's worked out all right. And now I'm founder and currently work as the CTO of Magdrive. Let's let people into the room. So in this talk, I'm going to talk about how satellites are built. I'm going to talk about Magdrive as a company and what we're developing. I'm going to then talk about how space is changing, because we really are on the precipice of the biggest change we've seen in the space industry and space in general ever. And then I'm going to finally talk about how you can pursue careers in the space industry if you're interested. So firstly, how do we build spacecraft? How do we operate them? And where do they live? Well, first of all, what is a spacecraft? Spacecraft are used for many different applications, such as Earth observation, communications, and navigation. And they are basically little robots flying around in space that we usually communicate to via microwaves. So think of them like RC devices in space. But they are already playing a major role in our daily life, with most of us interacting with a satellite or a satellite-enabled product every day, the most obvious example being GPS. But they're also becoming more prevalent in things like communication and in providing data, which is used by companies, from shipping companies to farming companies and everything really. So here's a little slideshow of how we actually build and launch the satellites. First of all, satellites are built in clean rooms. This is to minimize the amount of potential dust, which could cause your multi-million-pound device to break if you get a single hair shorting something out, for instance. So they build the satellite in the clean room. These then go through thermal cycling, vacuum tests, and even in some cases radiation tests to make sure that it's not going to get fried by the increased levels of radiation. Once you're happy with everything, you'll send your flight model to get integrated into the spacecraft. A very common way of getting small spacecraft up now is through ride shares. This is one of the SpaceX transporter missions, and it's almost quite comical. They'll have a central column, and then they'll attach lots of little satellites to it. And some of these satellites go on and deploy other satellites. For instance, this one is a deorbit ion cube, and that will carry lots of smaller satellites, which it will deploy later on. This is then launched. Here's a Falcon 9 launching up into space. This is one of the most extreme parts of the journey for your hardware. You're experiencing enormous acceleration, lots of vibrations, shock as bits of the rocket separate. And assuming everything survives, it gets deployed into space and you can start communicating with your satellite. It's not uncommon for satellites to die on the way up because of the extreme conditions. And then once you're in space, you'll be orbiting the Earth every 90 minutes or so. passing in and out of the shadow of the Earth and in and out of the sun. And that means that your device is under constant temperature strain. So, for instance, the tips of your solar panels can cycle between plus and minus 100 degrees every 90 minutes, which is fun for them. And then at the end of your life, you want to bring your spacecraft down closer to the Earth's atmosphere so that it can burn up. This will be usually after a few years of operation. There's new legislation coming in which requires satellites to deorbit themselves automatically within 5 years once their mission is complete. And once you come down to about 400, 300 kilometers, the atmosphere of Earth is thick enough that it will slowly decay your orbit and force you to come down very rapidly. In terms of where these satellites live, the vast majority of them are actually in low Earth orbit. So although space is big, we're actually putting all of our satellites into a very thin shell around Earth. These are all the satellites which are doing Earth observation, the rapid communication ones, which you might have heard of, like Starlink. It's also obviously where we put our space stations, and lots of these very small satellites, which are usually a bit cheaper, don't have electronics which are necessarily rated for the more extreme radiation environment further out. They'll all sit in low Earth orbit. And low Earth orbit's been where we've seen the big growth in satellites recently. But there is interest and rising interest in both medium Earth orbit, which is relatively unpopulated. You've got GPS there and a couple of other companies interested in stuff. And then geostationary orbit, where you have which is an orbit set distance away from the Earth such that you always stay over the same point. Now those orbits are extremely valuable, and there are a certain number of slots which companies will hold on to by keeping their satellite there. And lots of arguments have ensued from people arguing over who owns a slot. And they're used for things like communication, usually much larger satellites weighing several tons. However, space is changing, and it's changing rapidly. And this is primarily being driven by falling launch costs. You've got a little infographic there showing how space launch prices have gone down to about just over £1,500 per kilogram, or dollars per kilogram, with the Falcon Heavy. And that's potentially going to drop a lot further as things like Starship come online. All of these launch companies are effectively racing to the bottom to provide their services as cheaply as possible and as regularly as possible. And as space has got cheaper to access, it's fallen into the domain of small companies or university labs which can build and launch their own satellites. And this has caused the number of space objects to skyrocket. And there's a picture of that deorbit ion carrier I showed you earlier, deploying gazillions of little CubeSats. And as space becomes more and more congested, it becomes more risky. Not only do we have thousands of satellites in space, we have many, many more bits of space debris. And it's all going to more or less the same location, that thin shell around the Earth, which is about 1,000 kilometers thick. And, the numbers are just staggering. There's over 1 million objects which are 1 centimeter in diameter and over 100 million, which are over 1 millimeter. And these objects are traveling at extreme speeds. Your spacecraft is going about 7 kilometers per second in low Earth orbit, and so is the debris. So if there's a head-on collision, that's almost 14 kilometers per second. At those sorts of speeds, things don't deform, they explode on impact. And so even a collision from a very small bit of debris can be devastating to your mission, and that in turn can lead to more debris. So this is a growing problem which the industry has been well aware of for a long time. There is stricter legislation coming in to require spacecraft to deorbit and to avoid collisions automatically. And there are companies looking at trying to clean up bits of this mess, but it's a bit of a tragedy of the commons problem where no one wants to clean it up because someone else is going to mess it up. So next I'm going to talk about what we do at Magdrive, how some of the solutions we're working on can alleviate some of the problems and how we fit into the changing space landscape. So Magdrive is developing a new type of spacecraft propulsion. It's an extremely high thrust plasma propulsion. And although we've seen massive changes in launch, spacecraft propulsion really has not changed for 50 years. The electric propulsion solutions like Hall effect thrusters, gridded ion thrusters have existed since days of the Soviet Union, and they haven't moved on that much. They've got a little bit smaller, a little bit lighter, but they still only control a very small proportion of the market. And that's because they don't provide sufficient thrust or sufficient maneuverability to do a lot of the maneuvers satellites want to do. So that's what we're developing. We're developing an extremely high thrust electric propulsion system, which allows spacecraft to do all of the maneuvers they need to, but still maintains that high level of efficiency, or miles per gallon, which allows them to operate efficiently. So this is our new type of plasma thruster. It's a very efficient electric propulsion system with a very high thrust to weight ratio. We're looking at up to 100 millinewtons per kilogram, which is about 10 to 20 times higher than what you'll find with the best performing Hall effect thrusters. We achieve this with a metal propellant, which is vaporized into a plasma using a pulse power system. This plasma is then accelerated through a magnetic chamber, which allows us to direct and control our exhaust. Now, by developing this new type of propulsion, we think we'll be able to help address some of those problems we talked about earlier, with the massive increase in spacecraft going up and the massive increase in bits of debris. There's going to be a real need to increase the amount of times you need to dodge out of the way, basically. This is called a collision avoidance maneuver. They don't actually use the word collision. That's a big no-no. Conjunction is the word, because things don't collide. But the numbers of spacecraft going up means that we're looking at a factor of 100 increase in the amount of conjunctions over the next 5 years. And there's going to be an increasing need to rapidly avoid collisions. Existing solutions primarily use monopropellants or cold gas thrusters, and they don't have the sorts of miles per gallon or efficiency to be able to operate for a long duration if they're doing a conjunction avoidance maneuver every couple of days. So we need a system which is able to provide both that high thrust to do that maneuver, but also that high efficiency. But in addition to helping to solve that problem, we actually enable entirely new missions. There's a lot of interest in new types of close proximity maneuvers, which will allow spacecraft to maneuver close to one another to service and repair one another or to build large structures. These are maneuvers where you require a system which is both highly efficient to be able to do your mission many times and make your business model actually make sense, but also very highly maneuverable to be able to respond quickly. And we think that's where the Magdrive thruster is going to excel and enable an entirely new future in space. So this is the Magdrive team at our lab. We've built a world-class plasma physics lab based in Harwell, which is south of Oxford. We've got our own vacuum chamber, plasma diagnostics, thrust balancers. We've got our own clean room, which we used to build our recent flight hardware. We've actually grown to a team of 12 now, and this is all the old lab. We've moved to a much larger premises, 450 square meters, which is absolutely gargantuan. And we're not even using the upper floor yet, but we have plans to grow. And this is a little bit more detail on exactly what we're building. You can see one of our prototypes, one of our older prototypes at the back there. We give our prototypes stupid names. This one's called So Much for Subtlety because it was massive. And then this is the final product which we're aiming towards. And the metrics we're targeting are 100 millinewtons per kilogram at 2000 seconds of specific impulse. So that's a similar ISP that you find to those Hall effect thrusters, but with that magnitude improvement in the thrust weight ratio. By using this solid metal propellant, that makes things much, much easier for end customers. There's no heavy gas cells, no heavy chemicals, no potential explosives. So this makes the system much easier to install. The system can be delivered to the customer fully fueled and integrated into the spacecraft, simply with power and comms. It doesn't need to be filled at the launch site, which most systems do, which massively saves on the operational expenditure. We've reached TRL6 with a full prototype demonstrated inside the vacuum chamber. This is our vacuum chamber with our thrust balance. This guy is looking at absolutely nothing, just posing for the image. Behind him, you can see an image of a plasma being detonated. When we fire our system, we produce these little plasma bolts, these little bullets, and we do that many, many times a second. What you're seeing here is one of those plasma bullets actually traveling towards the camera. So you can't really see much, but it makes for a nice image. So now we've reached TRL6, we're focused on scaling the performance and reducing the mass, getting the system ready, hopefully for our first full system flight in 2024. However, we've actually already put something in space. Went up just beginning of the year, on the 3rd of January, on the SpaceX Transporter 6. This was a test of our power system. Now, due to the numerous delays involved in this. This hardware's like a year out of date now, and we're operating stuff which is way more powerful. But what we flew was a half U or 500-gram payload that you can see here in the bottom left. You can see the assembled version and then the internal electronics. And what we were keen to demonstrate there was, firstly, that our power system works, that we're able to draw power from the spacecraft, store it locally, and then discharge it through our pulse power system. But secondly, and probably much more importantly, that we could integrate our hardware into a customer satellite. So this was integrated into a 6U spacecraft that you can see being assembled there. And this allows us to get our first bit of flight heritage, proving that we as a company can deliver working flight hardware. And this is the first step towards future collaborations with customers and then eventually onto sales. You can see the rocket actually launching there. Magdrive's in a good position in terms of our supporters. We've been both successful in raising capital from private investors. So we did a $2 million seed round, which closed 2020. Somehow we did that in the pandemic, which is probably even more impressive. That was led by Founders Fund, which were the key investors in SpaceX when it was Musk and Mates, but also brings in 7% outside and Entrepreneurs First. However, since then, we've secured an additional 3 million of non-dilutive funding through European Innovation Council, the UK Space Agency, and the European Space Agency, and then been supported by a variety of other organizations such as Creative Destruction Labs, the ESA Business Incubator, and AWS Space Accelerator. However, small thrusters, these 1 kilogram systems, are just is specking out what this larger system would look like, this sort of dishwasher size system, which will probably weigh about 50 kilograms. With this, you'll be able to produce multiple newtons of thrust, which allows you to start powering much larger spacecraft, which are looking at operating in the lunar environment, in the cislunar environment, operating out to geo, and even going, not sure what happened there, even going out to other planets. And one of the real benefits of Magdrive is that our propellant is a metal. We are able to use a variety of metals, in particular aluminium, copper, iron, all of which are very prevalent in space. So there's a real chance to close the loop here, to recycle satellites, to mine asteroids or lunar regolith, and use those as our propellant source, which is something no other system can do. And yeah, by reaching further into space, Magdrive hopes to be the catalyst for humanity becoming a spacefaring civilization by firstly enabling us to start building things in space, allow satellites to service one another, which I'll talk more about in a little bit. And then in the future, helping to power these spacecraft which are going out to Luna and to other interplanetary destinations. So I'm going to now move on to talk more about the future of space. What's this new future that Magdrive envisions? How do we fit into that? And what are other people doing? So firstly, single satellites are out. They're on a fashion. No one talks about that anymore. It's all about constellations of thousands of satellites now. Satellites which cover every part of the world and are able to work in unison. Starlink is probably the most famous example. You know, Elon Musk wants to put 42,000 spacecraft up there. He's not alone. Amazon wants to do something similar. There's a whole bunch of different Chinese firms that want to do the same thing. OneWeb, the kind of UK firm, want to do something similar. And this is a different way of operating because here you're not worried about a single high value item. Instead, you have lots of individual satellites, which are quite cheap per unit, but you're constantly replenishing them. They may only be up there for 5 years. So you're constantly replacing bits of your network. And this makes your network modular and also makes it expandable, which is very attractive. And with this system, you're able to achieve, you know, internet anywhere on Earth, omnipresent Earth observation, where you can view the whole planet all the time. And these are quite powerful abilities, which lots of companies think will be very, very profitable. However, not only that, but we've new space stations coming up. The International Space Station is set to be retired beginning of next decade after 33 years of operation. It's apparently full of holes, and the astronauts keep complaining that it stinks. That's true, actually, they do. There's a fair few space stations which are looking to replace it, including the commercial ones, which are probably the most exciting real change in how we see and how we operate in space. So we have 3 commercial space stations, Orbital Reef, Starlabs, and the Axiom Space Station, which are all looking to come online about 2027. Somewhat ambitious goals, but let's see. The Chinese Tiangong space station is already operational. I think they're continuing to expand it and have bold ambitions there. And the Indian Space Agency is also planning a space station in the near future. Not only that, but there's a space station which is going to be put around the moon, which is pretty funky. So yeah, humanity is going back to the moon, and it's going to stay this time. This isn't just NASA, ESA, and everyone else is involved in this. The Lunar Gateway is this lunar space station, which is going to be in orbit around the moon, and construction is going to begin on that just next year, hopefully. The first Artemis mission, which is going to take humans back to the moon and help build this space station, launched just last year in November, I think it was. And that was an uncrewed test of the system. It was flawless, apart from destroying the launch pad. So I guess I'll rebuild that, but that's easy, maybe. And we're hoping for the first landing of humans on the moon in 2025. The reason why we're building a space station around the moon, though, is quite an interesting one, because we've never built on another planet. So no one really knows how to do it that well. Like, you know, the lunar dust is actually basically really tiny bits of glass and metal, which will play havoc with any machines. So that's a quite unique environment. However, we have become quite good at building space stations in space, the International Space Station being a good example. So this permanent presence in space is a good first foothold, which will then lead to hopefully a permanent lunar base. And it's not just big government agencies going out to the moon. There's a lot of commercial interest. There's been commercial satellites which have gone to the moon. The Artemis 1 actually carried a lot of commercial payloads with it, which it deployed in in lunar orbit. But one of the biggest and most exciting areas which we see expanding in the near future, and which Magdrive want to play a big role in, is the rise of in-orbit servicing and manufacturing. This is a very broad term, but we fundamentally believe that this is going to shape the space ecosystem in the next decade. And what we mean here is satellites which are able to repair, to refuel one another, to remove debris, but also build large structures in space. And this is a real game changer, because you're really restricted on how much you can launch into space and what you can launch into space by your launch vehicle. It's an extremely dangerous process with all those vibrations and whatnot. Lots of things die during that. And this massively adds to the cost. A good example is the James Webb Space Telescope. That had this incredibly complex folding mirror shape, which probably added an enormous amount to its budget. That was for 8 minutes of its life. Once it's in space, it unfolds and it's like that forever. Imagine if you could build that system in space, the savings that would be involved there, or if you could build a system which was 10 times as large for little modular blocks. So yeah, building large telescopes, large solar arrays, large antennas, these have all become possible. And this is the real game changer. And not only that, but we'll be making things in space which will have value for us on Earth. Space is a very unique environment with very strong vacuum, with you can reach very low temperatures relatively easily. And this means it's a perfect place to manufacture lots of items like fiber optics, like certain drugs. You can grow the crystals in 0G and they come out quite nice, apparently, from what I hear. And I think there's going to be a real ecosystem of companies with large factories out in space building and manufacturing items to bring back to Earth, and satellites which go around building these factories, repairing one another, refueling the factories. And in all of these systems, we need a space tug. We need something which is able to very reliably and very efficiently move things around, allow spacecraft to maneuver around to build things, and it needs to be responsive to be able to do that close proximity maneuver. And this is where we see the real value in what Magdrive's doing and what we're trying to enable. We want to enable this entire ecosystem out in space. And one of the really exciting results of that potential ecosystem is the prospect of space solar power. This was something which, until very recently, was a bit of a no-no in particularly NASA. It would be like a career ender if you started talking about it. But it's got a lot of very influential people looking at it very seriously, and the economic argument makes a lot of sense now. Solar power has got to the stage where it is viable to put it in space. Launch prices have come down low enough that this actually becomes economically viable. And the general idea is massive solar arrays, multiple kilometers long, far too big to launch. Obviously, you've got to build them in space, which are able to collect power 24 hours a day, 7 days a year, and beam it back to Earth via microwaves. The advantage of that is that you are now generating baseload power, which is much more valuable as a power source. And many people, myself included, believe that space-based solar power is going to play a pivotal role in allowing humanity to become to reach zero carbon emissions. Relying entirely on wind farms, I think it's going to be extremely challenging. We're going to have to throw some of these more exciting ideas into the mix, definitely. Again, this is one of the things that Magdrive wants to help enable the construction of through our new thrusters. So finally, I'm going to talk about the space industry. Hopefully I've told you how amazing it is and why you should come work in this industry. It really is right at the edge of transforming and just growing far beyond where it's been before. So yeah, space is already big business. It's no longer the domain of NASA. When you think of space industry, you might think of these guys here with their great bow ties. That's no longer the case. Space is a commercial entity. It employs almost 50,000 people in the UK alone. UK is a quite big player in space industry, and it's a much more diverse group. You've got engineers, you've got scientists, you've got business people, you've got even journalists, which focus purely in space. And yeah, the UK is a major player. We account for about 7% of the global industry. There are plans to hopefully raise it up to about 10%, which is quite ambitious. But one of the areas we really excel at is in satellite hardware. The US does all the cool launch stuff, which makes for great videos. But the UK, despite being a very small island, builds a fifth of all satellite hardware. Now, if you want to work in the space industry, I've got good news for you. STEM subjects, which you guys are presumably doing, are the most in demand. We've moved away from, you might have the stereotype image in your mind that everyone in the space industry has a PhD. That's no longer the case. It's still quite high compared to other industries. About 30% of the industry have a PhD, and almost 90% have a degree, usually in engineering or so. And yeah, space industry, last point, yeah, it's more diverse, less research focused with more commercial applications. Now, if you want to work in the space industry, very similar to pretty much any industry or any top company, you want to demonstrate that you are a self-driven student that's able to learn and progress projects on your own. I would say the two best ways to do this are firstly to start engaging with the space industry at a young age. You're even during your degree, you're in a perfect position to attend conferences like the UK SEDS conference, the Farnborough Space Tech Expo. And there's also internships that you can get through space companies. I would recommend having a look at the SPIN program organized by the Satellite Application Catapult, which are funded internships to work with space companies. And I would also highly encourage you to work on personal projects which go beyond your curriculum to demonstrate that you're able to do something which isn't just mandated by the university. Now, be this, build your own simulation, or you build your own robots based on Arduino stuff, or even there was one guy I knew who created all these amazing videos teaching thousands of people across the planet different core concepts of maps. But demonstrate that you are able to do stuff not just because you're told to do it, but because you want to. And my top recruitment tips, firstly, you will get approached by recruiters, particularly if you go do a PhD at Imperial, because you are a top candidate. Be careful of recruiters. Unless they have a proven track record, they're kind of a waste of time and can potentially do you more harm than good. You're much better off applying to companies directly. I'd recommend having a look at large companies, your big aerospace giants like Rolls-Royce, Boeing, Airbus and stuff. They have excellent graduate schemes where they'll put you in multiple departments, and it can be like a second degree, teach you proper engineering. But you can also get in touch with small companies like startups. Startups allow you to get involved in a lot more of the company's day-to-day operations. They allow you to grow with the company, and they allow you to have a much bigger say in how the company is run and how the engineering progresses. But yes, that third point, very similar to the last slide, very much embed yourself in the industry. You're never too young to start networking. The UK SEDS, which is the Student Space National Student Space Society, is organizing a conference next month. I believe it's free to attend online. Recommend you do so. I would also recommend doing what interests you. Don't worry too much about what you're going to do 40 years in the future. The whole idea of working for a single company for 40 years isn't a thing anymore. And your career will change and evolve as as you age. And yeah, lastly, that first job is hard. We've all been there. It is a numbers game. You've got to send so many CVs. Do not expect to reply from all of them. Companies are bitches. I try to reply, but sometimes I forget as well. And then finally, working at Magdrive. If you are looking for a job and you're looking to graduate, Magdrive is a wonderful place to work. We are one of the most innovative and fastest growing propulsion companies, probably on the planet, definitely in the UK. And we very much embrace that startup atmosphere. We're a very fast moving company. We've only been operating just over 2 years, but we have our first hardware in space. We've already grown to a team of 12. So we are moving at an incredible velocity. And, we have all those startup tropes and cliches, like we have free beer in the lab, and half the team are taking the day off for the 24th to spend the day playing Kerbal Space Program 2 when that comes out, myself included. But we have bold ambitions for growth. We're planning to be about 100 strong by 2025, so we are looking to bring on new talented engineers. The most interesting engineers for us are electrical engineers, embedded systems engineers, experimental physicists, system engineers. And if you are interested, come talk to me afterwards, or send an email out to info@magdrive.space and say why you're interested in having a look at our company. We're also looking to put some job specs on our website shortly. We meant to do that last month, but been a bit delayed on that. But being a small company, we're able to look at people more on a case-by-case basis. There is no HR department. And so if there's someone who is particularly interesting and takes our fancy, we'd just like to have a chat and better understand how you potentially fit into the company and bring benefit. And that is everything from me. Thank you ever so much for your time, guys. Any questions?
Right, thanks. Great talk. I think we'll take questions. First, we'll do questions in person, and then we'll see if anyone's got a question online. So if anyone's got anything to ask, Liam?
So when you said that you can use a variety of different metals as your propellant, like if you were, I presume there is a preferred one for when you're sending them off. So do you send them up with that, and then once they're in space, they could utilize whatever is available, or is that?
Yeah, I mean the in situ resource utilization for propellant is something which is going to be a future goal, because that propellant's going to require refinement and processing. We are able to use a wide variety of propellants, and different propellants have different performances. So lower Z materials like aluminium, you'll get a higher specific impulse, but a lower thrust to weight ratio. The one which we're looking at most interestingly at the moment is copper, and that's partly because it is a lot easier to work with. We can buy it quite easily. So it's as much driven by those engineering decisions as the performance. So copper will give us quite a good level of thrust per weight ratio.
If there's no more questions, I'll move online. Yep.
Just wondering, going back to that was fascinating. Just going back to the early days of your thinking, what actually was why did you start going in this direction? What was the stimulus or what catalyst?
Yeah. So now you may laugh, but we initially started off, before even thinking about companies, we started off with a thought concept, which was a purely electric launch vehicle. Now, a lot of developments need to be made, particularly in the power supply department for that. But if this was driven by some hypothetical fusion reactor, could you achieve an electric launch vehicle? And we came up with a type of propulsion system, which was based on this extremely dense plasma confined with a magnetic field. And we're like, wow, that's really cool. And then we started looking at the space industry as it is and found that there was a real need for high thrust electric propulsion. Electric propulsion has existed for over 50 years, but it's never really been able to break into the market and take more than 20% of the propulsion market, despite everyone for the last 50 years saying, no, this is the future, it's going to be electric. But it just doesn't provide the thrust or the maneuverability to do the vast majority of maneuvers you need to do in space. And so it's very common, if you fly, say, a Hall effect thruster, to also integrate a chemical system or a cold gas thruster to do those collision avoidance maneuvers or to do those other maneuvers. And now you've got two propulsion systems, and that's not twice as hard to integrate. That's probably 10 times harder to integrate.
Thank you.
I've got a question for myself. So for manned missions, you've got station keeping as a focus. What about interplanetary missions?
For manned missions, sorry.
So you imply that the bigger system could be used on space stations for, assume, station keeping, so you don't deorbit, or you can maneuver as well. What about interplanetary systems?
Yeah, 100%. So yeah, I mean, what Magdrive's trying to do is build a thruster which is going to be a bit of a jack of all trades. It's able to do all of the maneuvers. So it will not only just be used for station keeping, it'll also be used to build these space stations. And when it comes to interplanetary transport, we think our thruster will be suited to that. We're looking at some of the companies like Rolls-Royce, which are building their small microreactors, and looking at those quite interestingly, because that allows us to get a much higher power density when you go out to the outer solar system. Now they're quite early stage, but there seems to be a bit of synergy between when we'll be providing our larger system, like post 2027, and when they'll be bringing their small nuclear reactors into space, which will probably be maybe 2030.
And this is still much more efficient than the nuclear engines that they're suggesting.
So there's kind of two ways of doing nuclear propulsion. You have nuclear thermal propulsion, where you use a nuclear reaction or where you isotope to heat up a gas and expel that. That's not particularly efficient, but it's easy and you can get quite a lot of thrust out of that. The other way is nuclear electric, where you basically replace your solar panels with a nuclear reactor. And then you can use electric propulsion like Magdrive.
Okay, thank you very much. I'll check the comments on Zoom. Nope. Are there any comments on YouTube? Can you quick check? No. Okay. Well,
cool.
That's all today.
Any other questions?
Yeah. Well, I mean,
No?
you said like if anyone wants to have a chat with you, they can just come over.
Yeah, I'll be here for a little bit.
Yeah. I'll turn all this off.
Thanks for your time, guys. Pleasure talking to you.
Thank you for your time.